Welcome back to the Deep Dive. We're here to really get into the heart of some fascinating topics, cutting through the noise. And today, we are taking a, well, truly mind-bending journey. We're looking at quantum computing.
It's definitely one of those areas that pushes the boundaries. Our main source today is a great article from Horizon Magazine, and it features insights from Professor Andres Embanis. He coordinates the Quantum Computer Science Consortium, QCS.
Right, QCS. And the promise here is just huge. I mean,
Well,
think about the 2012 Nobel Prize citation for physics. It basically said quantum computing could change our lives this century as much as regular computers did last century. That's massive.
it really is. It's not just, a small improvement. Professor Ambinis calls it a radically new way of computing, not just faster, but something fundamentally different, promising speed-ups by orders of magnitude.
Orders of magnitude.
Mhm.
That's the kind of thing that's hard to even grasp. Like solving something in minutes instead of, what, billions of years.
Mhm.
So yeah, in this deep dive, we'll unpack what quantum computing actually is, how it's so different from the computers, you use every day. We'll talk about the potential, the challenges, which are pretty significant, and what the future might hold. Let's dive in.
Okay, so to really get why quantum is so different, it probably helps to quickly think about normal computers first. Classical computers. Your laptop, your phone. They work by switching electric current on or off. That's your 1 or 0. Binary digits, or bits.
Little switches, transistors.
Exactly. Tiny semiconductor switches. And you combine these switches, these bits, to do basic logic, and that scales up to run, well, everything we do on computers now.
Right, the foundation we all know. But quantum computing just, it throws that out the window, doesn't it? It rethinks the whole thing. Instead of just on or off, 0 or 1 is encoded in a quantum state.
Precisely. It's not just flicking a switch, it's shifting between different quantum states. And here's the really wild part, the core difference. A normal bit has to be either 0 or 1. No choice. But a quantum bit, a qubit, can be in what's called a superposition. It can actually encode both 1 and 0 at the exact same time.
Both, simultaneously. Okay, that's where my brain starts to ache a little. How do you even work with that if it's both at once?
It's definitely counterintuitive. Think of an atom maybe having multiple energy levels at once, or a photon having several polarizations. That's the kind of physical property they use to represent that both 0 and 1 state.
Wow. Okay, so superposition is one thing.
Yes, and that alone is pretty amazing. But then there's entanglement. This is the real kicker, the source of the incredible power. When you combine qubits, they don't just sit there in their own superpositions. They can become linked, entangled. This means if you do something, an operation, on just one part of this combined state, it instantly affects the whole system.
Instantly, across all the linked qubits.
Instantly. It creates this processor where the power grows exponentially with every single qubit you add. It's a completely different scaling compared to classical computers.
Exponential growth. Okay,
Yeah.
that explains the orders of magnitude speed-up potential. So if the physics allows for this kind of power, what are the problems? What kind of challenges are we talking about that need this power? What could these machines actually do?
Well, they're aimed at problems that are just completely impossible for today's computers, even the biggest supercomputers, things that would take millennia. The QCS consortium, for example, they're working specifically on figuring out which kinds of problems are the best fit for quantum computation.
Can you give us an example, something specific?
Sure. A really big area is quantum cryptography, developing new, highly sophisticated methods to make communication truly secure. In a world where data breaches are constant.
Yeah, that sounds critical.
Definitely. And another focus is just developing the quantum algorithms themselves. It's not just about building the hardware. You need completely new ways of thinking about software to actually harness that quantum power efficiently
Yeah.
and get those massive speed-ups they promise.
Right, the software has to be quantum too. Makes sense. Okay, the theory is mind-bending. But making one of these things, actually building a machine that controls these incredibly delicate quantum states, that sounds like a huge engineering challenge.
Oh, it is a monumental one. These quantum processes are extremely sensitive. Tiny vibrations, temperature changes, stray magnetic fields, they can all destroy the quantum state, ruin the computation. Professor Ambanis mentioned back then that early universal quantum computers might be room-sized.
The room size.
Yeah, but the hope is always to pack more power, more qubits into similar or maybe even smaller spaces eventually, but initially, big.
A room-sized quantum brain.
Yeah.
Quite a picture. Is there just one way to build them, or are people trying different things?
Lots of different approaches. Physicists all over the world are exploring various technologies. Some use lattices of atoms, held perfectly in place by lasers. Others trap photons, particles of light, in tiny cavities and get them to interact. Still others manipulate the spin of atomic nuclei using magnetic fields. It's a real race exploring different physical systems.
So lots of parallel paths.
Exactly. And that 2012 Nobel Prize we mentioned earlier, that was partly for developing the techniques to actually trap and manipulate individual atoms or photons at that quantum level. That foundational work is crucial for all these hardware efforts. But the main challenge across all these methods is scaling up. How do you add more and more qubits without the whole thing becoming unstable and losing its quantum properties? That's the billion-dollar question, really.
Okay, so massive challenges, but incredible potential. What about timelines? When might we actually see these things, these sort of room-sized brains, becoming practical?
Well, forecasting is always tricky in science, but Professor Ambainis, speaking back around 2013, had some thoughts. He reckoned maybe 5, 10 years from then. So we'd be talking, late 2010s, early 2020s to get quantum computers capable of simulating complex quantum systems.
Simulating quantum mechanics itself.
Right, which would let physicists explore fundamental science in ways impossible before. Then, looking further out, he estimated maybe a couple more decades.
Decades, so potentially 2030s or even later.
Potentially. For them to become more general purpose, universal quantum computers capable of tackling other big mathematical problems, it's a long road.
A long road, definitely. And it's important to stress, right? Even when we get there, these machines won't replace everything. Your laptop is safe.
Oh, absolutely. Your laptop is safe. Quantum computers won't be good for, browsing the web or writing documents. Most everyday tasks will still run on classical computers, which will keep getting better incrementally anyway. Quantum is for specific, really hard problems. But it's also worth saying some specialized quantum systems, maybe not universal ones, but task-specific ones, are already out there being sold and used for certain applications.
Really? Already?
Yes, early stages, limited scope, but the first steps are being taken commercially. It's not purely theoretical anymore.
That's fascinating. And maybe the most surprising thing, for me at least, from this whole area, is that this super futuristic research is actually helping us now with today's tech.
That's right. It's a fantastic, often overlooked benefit. These groups, like the QCS Consortium, while they're designing algorithms for quantum computers that might not exist for years, that process itself leads them to new insights, new mathematical techniques, new ways of analyzing problems. And these can often be applied to improve algorithms running on the classical computers we already have.
So wait, the work being done for these far-off quantum machines is spitting off improvements for, like, the computer on my desk or the phone in my pocket.
It absolutely can, and likely already is in subtle ways. The deep thinking required for quantum algorithms can sharpen our approaches to classical algorithms, too.
That's incredible. It's like exploring space travel and inventing Velcro along the way, but for computing.
Exactly. It's a brilliant example of how pushing the frontiers of basic science, even towards seemingly distant goals, can generate really practical, immediate benefits you didn't even expect.
Wow. Well, this has been quite the journey today, really diving into this radical shift quantum computing represents. From the weirdness of superposition and entanglement through the massive hardware hurdles to this long but promising future.
It really covers a lot of ground, from fundamental physics to practical engineering.
And it shows how it could reshape technology by tackling those impossible problems. It's genuinely awe-inspiring in a way.
It speaks volumes about human curiosity and ingenuity, doesn't it? Pushing these boundaries.
It really does. And maybe that spin-off idea leaves us with a final thought to ponder. If research into something this complex, this futuristic, like quantum computing, is already improving the tech we use right now in unexpected ways, what other cutting-edge science, maybe stuff we haven't even heard much about yet, is quietly shaping our immediate future? What other quantum leaps are brewing out there?
That is a great question. The future is always being built, often in the places you least expect it.